Hello, Professor.
This here will be our outline. We'll start with an introduction, going into the cycle of a star and the origin of a black hole. How do we detect a black hole? What happens if we fall into a black hole? Hawking radiations. In every star, including our dearest sun, molecules are subject to a constant fusion that releases a huge amount of energy. For the most part, a proportional balance is kept between this energy and the star's own gravity, and this prevents it from collapsing. However, for heavier stars, things start to get more interesting in an unexpected way. Stars are mostly an accumulation of gas, mostly of hydrogen collapsing from a cluster of gas clouds under the effects of its own gravity. As it contracts, more and more of the gas in its core collide with each other due to entropy with greater and greater speeds. However, the gas will be so hot, and thus the hydrogen inside coalesces to form helium. Instead of bouncing off each other, the heat released is what makes the star itself shine. In addition to that, the heat will increase the pressure of the gas until there is balance between the gravitational attraction and radiation. Next, we'll be showing you a representation of how the balance breaks down.
As Ahmed mentioned, there is usually a balance inside the star. However, for heavier stars, things are different. The heat and pressure inside the star allows for heavier elements like iron to be formed. And iron, when it's fused, doesn't generate any energy, but it does consume energy. So this buildup of iron inside the star creates an imbalance where gravity exceeds the radioactivity. So the star collapses on itself, and boom. Boom! There are actually other factors that contribute to creating a black hole. For instance, the Pauli exclusion principle, which is closely related to radioactivity. So we have here an atom, and inside this atom, each electron with themselves, they can't have the same orbital state and the same spin, which translate to angular momentum. Thus, this difference in states between them creates a repulsion outward, which helps create a kind of balance. However, for more dense stars, the gravitational pull towards themselves exceeds this small repulsion, or the Pauli exclusion principle, thus making the stars collide as they get more and more dense.
Another possible outcome was pointed where stars with a limited mass of about 1 or 2 times the mass of the Sun would end up with what we call a neutron star, where the exclusion principle is applied not between the neutrons, but actually between the not between electrons actually, but between the neutrons and the protons. Their density is as high as hundreds of millions of tons per cubic inch. Here we can take matters into perspective. Here, if we take something that is the mass of our Sun and translate it to a neutron star, it will be around here 20 kilometers. And if we take something that is the mass of our Sun into a black hole, it will be literally the half of that. And even to take, for example, a nice example that I like actually is when we take Earth's mass into a black hole. It will be as small as your earring that you're wearing right now, and it can be actually really interesting as a fact. Neutron star has some of the properties of an atomic nuclei, including density and being composed of nucleons, as it sometimes refers as a giant nuclei. However, the difference is that a neutron star is held by gravity, whereas a nucleus is held on by strong interaction force. Well, the stars with masses above the Chandrasekhar limit, which is 1.5 the mass of our Sun, on the other hand, prove that the exclusion principle couldn't hold the collapse of a star with a mass superior to that limit. But what would happen to such a star? Well, according to general relativity, that suggests that there will be no observational consequences that will be detected by the telescope. So, since the gravitational field of the star bends the path of the light rays in space-time, that means that the light cones are slightly bent inwards the star, and as the star contracts and the gravitational field in the surface gets stronger, the light cones also get bent more inward to the star. The light would appear dimmer and redder. Thus, we can see that the star has shrunk to a certain critical, when a star actually shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light itself is bent so inward that it cannot escape. According to the theory of relativity, nothing can travel than the speed of light. So if light cannot escape, that also means that nothing else can escape. That's logic. The gravitational force of the star is all concentrated in just one little point of space-time with infinite question mark. That means we don't know the density where everything is dragged together, where nothing escapes to reach a certain distance. This phenomenon by itself is what we call a black hole. And what we have at its boundaries is what we call the event horizon. That has a meaning, since it coincides with the path where light rays are bent so much that they fail to escape from the black hole's gravitational pulse. That is a black hole.
Even if black holes do not give off light, there is still a way we can detect them. A black hole still exerts a gravitational force on nearby objects. So rather than attempting to detect the black hole itself, we can detect its effect on nearby celestial objects. Astronomers observed many systems in which two stars orbit around each other due to their own gravitational attraction, as well as systems where only one visible star is orbiting around an unseen object. It might be merely a star that is too faint to be seen. However, in some of these systems, like the one called Cygnus X1, that have also high emissions of X-rays, the most logical explanation scientists have found for this is that as the matter from the visible blows off and falls into the unseen objects, it develops a spiral imitating X-rays and heat. And for this mechanism to work, the unseen object has to be incredibly small, like a white dwarf, a neutron star, or a black hole. However, in the case of Cygnus X1, the lowest possible mass of the unseen object is 7 times the mass of the Sun. Thus, the only possibility that remains is that it will be a black hole.
So what happens if you fall into a black hole? Which is very probable, so be careful.
No, it's not.
It's not. It's not. But if you do fall into a black hole, this is what will happen. This is called spaghettification. It's actually the scientific name. It's actually the scientific name for it. And inside the black hole, as you know, there's a huge gravitational force, which is the existence of it in the first place. So it's so big that even the slightest distances in a body have different gravitational poles on them. So the gravitational pole that is here is different from the one here and the one here. So the person would theoretically get stretched and he would die.
Okay, we're gonna take a look at Hawking's radiation phenomenon, which is a really interesting phenomenon, by the way, that was discovered just a few years ago, that talks about how actually those massive stars can evaporate. So basically, as powerful as black holes are, there is this process that I just talked about. And to understand how it works, we should actually understand how empty space works, which is kind of contradictional to this. So basically, we have to look at empty space, and after that, we should see that empty space is filled with those virtual particles that are popping into existence and annihilating themselves, which is like a kind of way of seeing particles and antiparticles. So basically, when this happens right on the edge of this black hole here, as we can see, see that the particles are drawn into the black holes, and the other will escape from the black hole, and that the one that escapes from the black hole is what the real particle. So the black hole basically loses energy here, and after that, we can see that this is actually incredibly slow when the black hole is really massive, but it gets really fast when the mass gets smaller and smaller. So basically, for example, let's see, if we take a mass of a black hole that is as equivalent as the mass of an asteroid, we can see that it radiates as this room temperature. Right, and when the black hole has the mass of a mountain, it radiates about the heat of our sun, which is incredibly big. And at the last seconds of its life, the black hole radiates away with energy, billions of nuclear bombs with a huge explosion. And this process is incredibly slow. So, for example, the black holes that we know may take a googol year to evaporate, which is incredibly long. Talking about like 1 and followed with 100 zeros. So nobody actually will be here to witness it. So the universe will be most likely inhabitable by then. So yeah, this is basically how they die, and I hope it was interesting in a kind of